All right, this is problem 14 from chapter 17. And in chapter 17, problems 14 through problem number 17 are all part of the same thing. They are for ball screws instead of for a normal power screw with a stationary thread. So this is chapter 17, and we will work problem, let's do it this way, 14 through 17, because they're really all the same thing. Okay, page 592. A ball screw for a machine table drive is to be selected. The axial force to be transmitted by the screw is 600 pounds. So there's our F, 600 pounds. The table moves 24 inches per cycle. And is expected to cycle 10 times per hour. Let's see, for a design life of 10 years. And it says to select, for this problem, just select an appropriate screw. All right, so just like ball bearings, a ball screw's life, it follows the load life equation, right? The higher the load, the shorter the life. The more cycles, life is measured in cycles, basically. So you'll recognize the load life equation if you go back to page, here it is, page 589, equation 1712. You recognize the load life equation there. And basically, the bigger the thread, the longer it can last, or the higher load it can move. Now, page 590 is the only page where we have data for various ball screws. So figure 17.8 is the figure we'll have to refer to in order to answer this question. But first of all, the life we're looking at here, instead of being in revolutions like for regular ball bearing, the life that we're talking about here is the number of inches, essentially, that the thing moves in its lifetime. Does that make sense? Okay. If you end up, by the way, if you end up doing anything in CAD as a job, you may want to consider getting some mouse tracking statistics, because what it'll do is it'll track all the motions that you make in the X, Y. You'd be surprised how far you move your mouse doing a lot of CAD work. And the small movements of the mouse distance add up to quite a bit of distance. But anyway, so we're trying to add up how much distance this lead screw moves its load. So basically the travel is what we want. And the travel is 24 inches per cycle multiplied by 10 cycles per hour. So you see the cycles go away. Multiplied by 24 hours a day. We're just trying to get the total number of sorry, I can't write and talk at the same time. There's days per year. And then finally, 10 years worth of life. Okay, so multiplying all that out, you find that this is a total travel of 2.10 times 10 to the 7th inches. That's the distance that this screw is going to move in its lifetime. Now, at 600 pounds, basically, what we have here is a data point, right? We have a load and a life. The life is measured in inches. So go to figure 17.8 on page 590. And basically what we need to do is select a size screw that can handle this. So the travel life, if you look on the x-axis, what do we have? We have 2 or so times 10 to the 7th. So we look at 10 to the 7th, that's 1 times 10 to the 7th. Go to the next line, the next minor division line, would be about 2 times 10 to the 7th. And then go up to a load on the y-axis of 600 pounds. Now be careful, because both the x and the y-axis on this figure are logarithmic. And so if you go up, let's see, 100 is the bottom line, 2, 3, 4, 5, 6, 100 pounds. Let's see, looks like we're above the specifications for a 1/2 inch nominal diameter, so we'd have to bump it up to a 3/4 inch ball screw. Does that make sense? You guys see
The
it?
bottom line is 1.
not the bottom curve, but the very bottom line, the bottom horizontal line is, I'm sorry, it's not 1, you're right, it's 100.
So that next line, the first line up would be 1, 2, 3, right?
The next line up would be 200. Here, for the sake of the video as well, I'll point it out. So basically the bottom line down here, since this is logarithmic, is 100 pounds. You go up to the next division line, which is a gray line instead of black, and that's 200 pounds.
Okay.
Does that make sense?
Yeah.
We have 600 pounds, and so that data point of 600 pounds and 2 times, or 2.1 times 10 to the 7th ends up above the curve for the half-inch nominal size ball screw. So we have to go up to the 3/4 ball screw. Does that make sense now?
I don't get that. What is the quarter? Yeah, but you.
Okay, so we're going to take a 3/4, 2. Notice it's two threads per inch. So basically, if you rotate this thing twice, that would move the nut by 1 inch. So there's the ball screw that we're going to select. And so, of course, the lead is obviously just 1 over this, and the lead is just a 1/2 inch. So if you rotate the screw 1 time, it will move the nut by a 1/2 inch. Okay? All right, let's read the next problem, which is really just a continuation of this one. Question 15. For the screw selected in problem 14, compute the torque required to drive the screw. Okay, now in this case what we're talking about is the torque to move up against the load. So that's equation 1713. Now you have to be careful because there's an assumption built into this that the efficiency is 90%. And so for this question, the torque required, I'm going to write it this way, FL over 2 pi E, to make it clear that the efficiency is 90%. So I'm using equation 17.7, but equation 17.13 will give us the same result. Does that make sense? I'm on page 590, by the way. Okay, so the force being applied is 600 pounds force. The lead is a 1/2 inch, 2 pi, and efficiency of 90%. Then this gives us about 53.1 inch-pounds force of torque. One thing you can do for practice, if you're interested, is to figure out with this load what size Acme thread would you need and how much torque would it take. What do you think you'll find? Would you find that you need more or less torque? More. In fact, you need a heck of a whole lot more. Okay, because remember the Acme threaded screws are 20 to 30% efficient. This is going to be 90% efficient or more. Okay, next question. Question 16. For the screw selected in problem 14, the normal travel speed of the table is 10 inches per minute. Compute the power required to drive the screw. Now, I've thrown this in, or I've added it in because your author adds it in the context of an example problem, but that's the only place he put it. So all we're going to do is use the torque speed equation again. You have to be a little bit careful here though, because notice that what was given was the velocity, which is a linear velocity. We really need the rotational speed of the shaft. So the velocity that was given was 10 inches per minute. So how do we get the rotational speed of the shaft in? Well, let's see. The speed has to be in revolutions per minute. We know that there is 1 revolution per 1/2 inch of lead, right? All I'm doing is I'm relating rotation back to linear motion, right? There's 1 revolution per 1/2 inch because we figured out that was the lead. If you then multiply that by 10 inches per minute, you notice that the inches go away and we're left with revolutions per minute. So I just used the units to figure out the speed. So this is straightforward, right? This is just 20 revolutions per minute. And that should make sense, right? Because if you have to rotate the shaft by a half, or by 1 rotation to get a 1/2 inch of translation, you'll have to rotate it 20 times in a minute to get 10 inches per minute of travel. Right, so it's trivial stuff, but something that can trip you up if you haven't seen it before. So the torque we calculated before is what will go into this equation, and now we have the rotation speed. So we can figure out the power required, and it's 53.1 pounds force, I forgot my units, times the speed, which is 20 RPM. And what does that 63.025 do? It's a conversion factor, right? Yes, sir.
Where'd you get your 10 inches per minute though?
That was given in the problem statement that we just read.
Oh, okay.
Yeah, they just said if it moves the table at 10 inches per minute, then how much power is required. So what does that 63.025 do for us?
Versus it from.
Second
Horsepower?
Converts it to horsepower, right? That's all it does. So anyway, this comes out to about 0.017 horsepower. It's not much at all. Now let's do something else that's not in the book, but that I think will be useful. You could also write power as force times velocity, right? And the amount of force is 600 pounds force. The velocity is 10 inches per minute. Okay, now we're going to use we're going to need a conversion factor, but it's pretty easy, right? We can figure this out. There's 1 foot per 12 inches, and there is 1 minute per 60 seconds. Now what we have is foot-pounds force per second. You guys should have this committed to memory. There are 550 foot-pounds force per second for each horsepower. So the seconds, the foot-pounds force, and the feet are all gone. We're left with horsepower. So grab your calculator and plug in these numbers. Now, do you think you're going to get the same power, more power, or less power? What do you think will happen?
Same to do the same.
Let's find out.
We're close.
I must have done something wrong. Let me try again.
We got a little bit less.
0.015. Is that what you guys got?
Yeah.
Rounding down. Why would there be a little bit less power here and a little bit more power? Oh, it's horsepower, by the way. Here. Why the difference? This is power input, right? We're putting power into the ball screw by twisting it. Remember, the ball screw is only 90% efficient. So only this amount comes out. Take the number you have in your calculator and divide it by 0.9. And you'll get this number. Okay? So that's where that comes from. So basically this is the power input and that's the power output. Okay? All right. Got one more part to this. It's question 17. If the cycle time for the machine in problem 14 were decreased to obtain 20 cycles per hour instead of 10, what would be the expected life in years of the screw originally selected? So all of a sudden we've decided we need this to run faster, we need to do more cycles per time. And so now, management, I guess, has said, oh, we got to bump up the cycle time on this and get it to operate quicker. So how long will it last now? Remember, it was originally designed for a life of 10 years. So now what we have to do is go back to figure 17.8 on page 590. Now the load has not changed, right? The load is still 600 pounds, so we're still on the same horizontal line. And basically this is a log-log plot of the load life relationship, which is equation 1712. So if you go to 600 pounds, let's see, 100, 200, 300, 400, 500, 600, what you have to do is go over to to the curve for the screw we're actually using, and then read off the life expectancy. Okay? So when I do that, I get about 1.5, 1.6 or so times 10 to the 8th. Does that make sense?
Can you say that again?
Okay. We know what screw we're using, right? So what we're going to do, we know we still have a load of 600 pounds. So 100, 200, 300, 400, 500, 600 on the y-axis. Go over to the curve for the screw we're using, which is this third curve up, and read off the x-axis. When I do that, the best I can read is about 1.6 times 10 to the 8th. You see that?
Yeah.
It looks like 1.5, but remember this is a log plot, and so you have to take that into account as well. Okay? So I said the travel life will be about 1.6 times 10 to the 8th, and that is in units of inches. Now, if I take this and try to figure out how many years it'll last, 1.6 times 10 to the 8th inches, we've got now one cycle per 24 inches, right? That'll take care of the inches. And they've changed things so that now it's 20 cycles per hour. So that's 1 hour per 20 cycles. Right? That takes care of the cycles. And then there's 1 day per 24 hours, and of course 1 year per 365 days. And so plug in all that in your calculator, you'll get the life in years. And what I got was a life of 38 years. Okay? Questions? Okay, just like we did the last problem, I'm going to extend this one a little bit because there's something else that we haven't touched on in the chapter, and that is the critical speed. So go to page 591, look at equation 1715, and again, these are not in my notes, so I will need some calculator help. But let's assume a length for this. How long do you think the lead screw would be? This ball screw. Well, if we got a 24-inch per cycle, why would you make it much longer than that, right? So let's assume that it's a 30-inch length. Is that reasonable? Because you've got to support it at either end. You've got to have bearings and things. And so that you have a total travel of at least 24 inches, we'll add 3 inches on each end. Okay? So let's assume that the length, L, between supports is 30 inches. Now, the critical speed...
But it's between supports?
Yes, that's the length that's suspended. So basically, you've got a table that needs to move back and forth. There's a nut on that table, and you use a ball screw to move it. Okay? You're going to, of course, have a motor or a gearbox or whatever coupled up to the ball screw, but you've got to support the ball screw. Right? You need a travel distance of 24 inches. Since I'm making this up off the cuff, I'm just assuming that the length between the supports is 30 inches. Does that make sense?
Okay, yeah.
Okay. All right, the reason this is important is because that, basically these bearings help hold the shaft, they support it. And it's the area between this that's going to deflect. This can't deflect, right? Okay, so to calculate the critical speed, I guess I've got the length up there now. So to calculate the critical speed, we'll use equation 1715, 4.76 times 10 to the 6th times D times Ks divided by a safety factor divided by the length squared. Now what is all this stuff? Well, basically this 4.76 times 10 to the 6th is a big conversion factor. D is the minor diameter of the screw. Basically what we're doing here is we're assuming that the screw is acting like a rod whose diameter, for the sake of bending, is the minor diameter. I mean, think about it. if you have a rod with teeth on it, those teeth aren't going to do much to prevent flexing, right? They won't provide a whole lot of support. So we're just going to deal with the minor diameter, and that's something that's listed, at least for the Acme and the square threaded screws. Now, in our ball screw, we don't have the minor diameter. The nominal diameter is not equal to the minor diameter, and unfortunately we don't have it. So just for the sake of this problem, let's go back. Well, I don't want to be confusing. If I go back and make an assumption that we've got an Acme threaded screw, that's going to be confusing. Let's just use the nominal diameter as if it's the minor diameter. So 3/4 inches. We just need a number we can plug in here. So 0.75 inches, and that's part of this conversion factor here. We'll plug in inches, a dimensionless fixity factor, a dimensionless safety factor, and length here in inches, and we'll get out the speed in RPM. That's the critical speed. Okay, so the fixity factor, what's that? Well, remember when you studied columns buckling, the way that they deflected, I've already drawn on the board, there were several different modes, right, depending on exactly how the ends were fixed. Now let me change colors. If these bearings are self-aligning bearings, then what they're going to do is allow the ends to rotate. And then the deflection will look something like that. On the other hand, if they're not self-aligning, then they're going to prevent the shaft from flexing until you get out, or well, it'll prevent the ends of the shaft from rotating, is what I should say. We could have a self-aligning bearing on one end and a fixed on the other. It just depends. Okay? What would you need in order to make sure that this critical speed is very high? You want both ends fixed. If both ends are fixed, then what will happen is it'll take more force to get it to deflect, right? And that means a higher speed, basically. On the other hand, you may want to make this number low, because a lot of times what people will do when they design a shaft, if it's to be operated at speed continuously, what they would do is they would just accelerate through the critical speed very quickly, so it doesn't get very many rotations at the critical speed, and therefore does not deflect very much. Now in this particular application, I would prefer to make it very stiff, because if it's moving this table back and forth, it's accelerating and decelerating many times per day. I don't want to accelerate through the critical speed unless I know that I'm going to, within the first 1/8 of an inch or so, I'm going to accelerate up to full speed and then travel at that speed.
So you can get past that critical speed.
Right. Now, it depends on the application to decide exactly what you're going to do. Yes, you can accelerate as long as you go through the critical speed very quickly. It really won't matter. Okay. But since this is an application where I assume we've got a lot of starts and stops, I'm going to say that I would want not self-aligning bearings, but bearings that are rigid so that I can make the critical frequency go up. Okay. So what you'll notice is that on page 591, look on the left-hand column beneath equation 1715. Simply supported at each end by one bearing, that's not what we've got. Simply supported would be where both are self-aligning. You may want to make a note of that. One would be self-aligning bearings on both ends. 2, fixed at each end by 2 bearings that prevent rotation at the support. So these are, for lack of a better word, rigid bearings, right? They're going to prevent rotation at either end. That's what I would prefer. Notice that that's the one with the highest size factor. Highest fixity factor. We use KS for size factor in gearing. I'm trying to read and talk and think at the same time. Notice also option 4 is fixed at one end where it can't rotate and free at the other. You could have a ball screw that just is cantilevered out. And in that case, the fixity factor is low. For our case, I'm going to choose that both ends are bearings that prevent rotation. So basically, the factor I'm going to put in here is 2 point, thanks. Okay. All right, safety factor, let's just set that to 1. And then the length of the shaft is 30 inches, and that has to be squared. Okay, so now let's grab the calculator and find out the critical speed. Okay, so 4.76 E6 times a quarter times 2.24 divided by 30 squared. 8,885 RPM. So basically, I would be concerned when we reached about 8,000 RPM. Questions? Obviously, even though this is a ball screw example, this would apply for Acme threaded screws, any screw thread, really any shaft. It's just a simple cylinder. All right.